This observation shows bright deposits and channels in the Thasia Plateau region on Mars. The plateau is a vast sloping volcanic plain partly surrounded by rugged highlands, mostly of Noachian and Hesperian age in the western hemisphere of Mars. It is the most extensive component of the Tharsis Rise, a vast volcanic plateau centered near the equator in the western hemisphere of Mars by area. Channel systems, upturned beds, and large troughs occur in places along the southern edge of the plateau, and in the southern part, the lowlands that surround the plateau include heavily cratered highland terrain and relatively smooth, low plains. Some geologists have suggested that the Thasia Plateau, which stretches over 2,000 kilometers across the Martian surface, was once a large, ancient drainage basin predating the extensive volcanic formation of the Tharsis Rise. While slowly climbing the slopes of Mount Sharp recently, Curiosity rover discovered large deposits of carbon locked away in carbonate minerals. This find suggests that the red planet was once warmer and habitable. Carbonate minerals form when carbon dioxide interacts with water and rock, making them an important marker of past environmental conditions. Scientists have spotted these minerals before on Mars by rovers on the ground, orbiters above, and even in Martian meteorites that fell to Earth, but Curiosity's latest data adds exciting new details. It tells us that the planet was habitable and that the models for habitability are correct. The minerals found by the rover likely formed in extremely dry conditions through chemical reactions between water and rock followed by the process of evaporation. This process points to a time when Mars had a thick enough atmosphere, rich in carbon dioxide, to support liquid water on the surface. However, as the atmosphere thinned, that carbon dioxide would have begun turning into stone. One standout mineral in Curiosity's new discovery is siderite, an iron-rich carbonate found in surprisingly high amounts, between 5 and 10% by weight, alongside salts that dissolve easily in water. The broader implications are that the planet was habitable up until this time, but then, as the carbon dioxide that had been warming the planet started to precipitate as siderite, it likely impacted Mars's ability to stay warm. What makes this find even more fascinating is the presence of iron oxyhydroxides in the same deposits. These minerals suggest Mars may have once also had a functioning carbon cycle, similar to Earth's, where some of the carbon dioxide locked in rocks eventually made its way back into the atmosphere. By comparing Curiosity's findings with orbital data, scientists believe similar layers across the planet could have trapped up to 36 millibars worth of atmospheric carbon dioxide, enough to dramatically change Mars's climate. This Martian discovery also ties in closely with work being done right here on Earth. Scientists have been exploring ways to combat climate change by turning human-made carbon dioxide into stable carbonate minerals, essentially locking carbon away in rock. So what scientists are trying to do on Earth to fight climate change is something that nature may have already done on Mars. Learning about the mechanisms of making these minerals on Mars helps us to better understand how we can also do it here on Earth. This observation shows part of the northern slope of a 6-kilometer Bond crater on Mars. Pole-facing gullies have eroded the northern slope of this small crater, located just west of where Usbo Falls, a roughly 365-kilometer valley, emanates from Bond and continues in a northerly direction. However, Hale Crater, a large 125-kilometer crater to the south, has numerous gullies on its slopes and even on its central peak region. Unlike some other gullies on Mars, these are in light-toned materials. Gullies on Mars occur on steep slopes, especially craters. They are believed to be relatively young because they have few, if any, craters, and they lie on top of sand dunes which are young. Usually each gully has an alcove, channel, and apron. Although many ideas have been put forward to explain them, the most popular involve liquid water either coming from an aquifer or left over from old glaciers. Researchers have analyzed both Bond and Hale craters to try to determine why Bond has no gullies on its slopes, except for a small 7-kilometer crater on the floor in its central area. The gullies in this observation have eroded into bedrock layers, forming tributaries in the upper slope region and distributary channels further downslope on the debris fans. Research attributes these features to fluvial processes. This amazing panorama was taken within the Jedis Valley's channel on Mars. At left of this view is Curiosity rover's robotic arm, which is raised after drilling a hole at the location. The samples collected here could help scientists understand how this area formed in the past billions of years ago. Jedis Valleys was likely formed roughly 3 billion years ago by large floods of water and debris that piled jumbles of rocks and sediment into mounds within the channel and created a long ridge downhill called Jedis Valley's Ridge. NASA scientists are also interested in the ridge because the ridge sits at the base of Mount Sharp, and it includes many boulders that were washed down from much higher up the mountain, where Curiosity won't be able to reach. The white stones visible in the center of the observation have captured the attention of scientists because after Curiosity drove over one of the rocks, pure sulfur crystals were discovered inside them. The rocks don't appear to fit with other materials seen in this landscape, so it's possible that the stones were formed here, or they may have been brought by floodwaters or avalanches long ago, even coming from locations high above Mount Sharp, which Curiosity is climbing at the moment. The yellow sulfur crystals found inside the rock marks the first time pure sulfur has ever been found on Mars. It isn't clear what relationship, if any, the elemental sulfur has to other sulfur-based minerals in the area. While people associate sulfur with the odor from rotten eggs, which is the result of hydrogen sulfide gas, elemental sulfur is odorless. It forms in only a narrow range of conditions that scientists don't associate with the history of this location.